Imagine walking into a boardroom, right? You put $1 billion in cash on the table, and you bet it entirely on what the world will look like in exactly 5 years.
Oh, wow, yeah. That is quite the visual.
Right. And I mean, if you're right, you completely dominate the global market. But if you're wrong, your company goes bankrupt, your employees lose their jobs, and you are just entirely finished.
Yeah, which sounds like, insane gambling to most of us.
Exactly. But in the high-stakes world of corporate strategy, that's just a Tuesday.
It really is. And, if that billion-dollar factory or that massive supply chain overhaul is built on just a subjective hunch like someone's gut feeling that happens to turn out wrong, well, the financial and operational consequences are absolutely disastrous.
Which brings us to our mission for you today. Welcome to this deep dive. Today we're opening up a really fascinating, rigorous academic text on quantitative analysis for managerial applications. Specifically, we're looking at how organizations navigate an incredibly uncertain future.
Yeah, because the future is messy.
It is. So we're going to demystify how businesses predict the unpredictable. We'll track how leaders evolved from basically engaging in primitive crystal gazing, trying to read the tea leaves of the market, to developing highly complex, rigorous scientific models.
Right, the real hard math.
Yeah, exactly. By the end of this, you'll understand how companies anticipate everything from next month's warehouse inventory to the technological landscape 20 years from now. Okay, let's unpack this.
Right, and to really unpack it, we have to start with the foundational insight from our sources. True forecasting is not just guessing. It is a highly structured scientific discipline.
Right.
I mean, a prediction might be a subjective hunch, but a true forecast relies on historical data, very explicit assumptions, and mathematically sound models.
Right, but if you're listening to this, you might be thinking, look, I know business is messy. You can't just plug human behavior into a calculator.
Oh, absolutely.
And you'd be right. I mean, we can calculate exactly where Mars will be in the sky a decade from now down to the millimeter. But it's incredibly difficult to know how many umbrellas a retail chain will sell next spring.
Exactly. And the text addresses this head-on by distinguishing between deterministic systems and complex economic systems. So, classical physics is deterministic. You know the rules, you get the exact outcome.
Right, like dropping an apple.
Right, exactly.
Yeah.
But an economic system operates in a reality where millions of interacting variables are just constantly shifting. To forecast something as simple as umbrella demand, a business has to wrangle competitor pricing, advertising budgets, unusual weather patterns like sudden floods or prolonged droughts, and even broad social upheavals that impact disposable income.
So it's like the difference between someone saying, I think it's going to rain tomorrow because my left knee aches.
Yeah, exactly.
Which is, a subjective prediction based on hunch, versus a meteorologist running massive atmospheric pressure models on a supercomputer to generate an actual forecast.
If we connect this to the bigger picture, the true value of that scientific forecast is its absolute objectivity. Subjective predictions do have their place, particularly for incredibly complex, highly abstract long-term decisions where hard data just doesn't exist yet.
Sure.
But a scientific forecast, as the text emphasizes, is essentially a computer program. Anyone can run it. Regardless of whether person A, person B, or an algorithm processes the numbers, the methodology ensures the output is identical. It basically strips the ego and the guesswork out of the mechanics.
Okay, so if we've removed the ego and established this objective baseline, how do businesses make those really massive bets for 5 or 10 years down the line?
Right, the long-term stuff.
Yeah. Like, let's say you're a government planner in the developing country or an executive building a manufacturing plant. How do you project what infrastructure you'll need a full decade from now?
Well, that specific challenge falls under technological forecasting. What's really fascinating here is the mechanics of how technology actually scales, because it almost never grows in a steady, flat, predictable line. The text specifically highlights a phenomenon in developing countries called leapfrogging.
Meaning they don't have to reinvent the wheel?
Precisely. Because of technology transfers and importing existing know-how, developing nations often skip entire stages of costly, slow development. As a result, many technological variables don't just grow. They show aggressive exponential growth.
Wow, okay.
Yeah. The sources note that when forecasters plot the logarithms of these variables against time, which is basically using math to unbend a massive hockey stick curve so they can read it as a straight linear trend, the explosion becomes incredibly clear.
And the sources provide some very vivid historical examples of this exponential explosion to prove the point.
They do, yeah.
Like, they track the historical passenger kilometers carried by Indian Airlines. The massive spikes in the amount of fertilizer applied per hectare of cropped area, and the installed capacity of electricity generation, which is measured in millions of kilowatts, all of these metrics didn't just tick upward, they skyrocketed.
Right. It's a massive curve.
But wait, I have to push back here. Nothing grows forever, right? I mean, you can plot an exponential curve up to the moon, but eventually everyone who wants to fly on an airplane already has a ticket. A farmer eventually runs out of physical land to fertilize.
You are entirely correct, and the mathematical models actually account for that physical reality. Unchecked exponential growth always hits a ceiling. This introduces what the text calls S-curves.
S-curves, okay.
Yeah, if you visualize it, a new technology starts out very slow at the bottom of the S because of initial bugs, high costs, adoption hurdles, that sort of thing.
Yeah.
Then it hits that exponential vertical climb in the middle when it becomes reliable and wildly popular.
Right, the boom.
Exactly. But eventually, it reaches a maximum limit market saturation,
Right.
and the growth levels off at the top, creating that S shape. Finally, it declines as the technology becomes obsolete.
So the math actually builds in its own limits. How do they calculate that ceiling, though?
Well, the text highlights specific mathematical models designed just for this. For example, forecasters use the Gompertz growth curve to model things like hydroelectric power generation.
Okay.
There is a hard physical limit to how much water flows through a river, right? So the curve adjusts its slope to reflect that absolute cap. On the other hand, they use the Pearl-type growth curve to forecast the number of electrified villages over time, which has an entirely different type of saturation dynamic. The model forces the business to acknowledge the natural limit to growth.
That makes total sense for things we can measure.
Yeah.
But if I'm planning for a distant future that lacks hard numerical data, and these mathematical S-curves have their physical limits, how do we factor in human wisdom?
Ah, right.
Because you mentioned earlier that subjective predictions still have a place. But if you've ever sat in a corporate strategy meeting, you know that gathering expert opinions usually just means the loudest person in the room gets their way. How do models prevent that individual bias?
That is where advanced scenario planning comes into play. Specifically, a method the text calls the cross-impact technique. Instead of asking one person to just guess the future, this technique explores the mechanics of how different potential future events interact with each other.
Oh, interesting.
Yeah, it asks, if event A happens, how precisely does it change the mathematical probability of event B happening?
So it's like mapping out a giant web of dominoes.
Yes, exactly.
Yeah.
The text gives a very stark example. Imagine a scenario where a war suddenly breaks out. That single event leads to vastly increased defense spending.
Right. Naturally.
But if we map the cross-impact, that increased defense budget simultaneously leads to a severely reduced emphasis on rural uplift and social development programs. You systematically map out these interacting scenarios to see all the possible cascading futures.
Okay, I understand the web. But my question still stands. How do you get a room full of highly paid, highly ego-driven experts to agree on those probabilities without it turning into a total shouting match?
Well, this is exactly the problem the Delphi method was designed to solve. And the mechanics of it are brilliant. You assemble a panel of world-class experts, but they never actually interact directly. There is no boardroom.
Wait, really? No boardroom at all?
None. An impartial coordinator sends them very specific, measurable questions. They aren't asking broad philosophical questions about the future of humanity. They ask things like, in what specific year will fiber optics become a commercial viability for mass communication?
And because they aren't in the same room, nobody can dominate the conversation.
Exactly. The experts send their answers back entirely anonymously. The coordinator takes all those answers and analyzes them statistically. They find the most optimistic date, the most pessimistic date, and the general distribution of everyone's guesses. Then, they send that statistical summary back to all the experts. Seeing the group's anonymous thoughts, the experts are asked to revise their initial estimates. It's an iterative process that goes back and forth until the responses stabilize into a solid consensus.
That is an incredible psychological hack. I mean, it effectively blindfolds the CEO and the junior analyst, making the outcome care only about the merit of the idea, not the title or the volume of the person saying it.
Right, it strips away the bias of reputation and the pressure of dominant personalities. And the sources also note that for shorter-term, localized forecasting, companies use opinion polls. They aggregate the intuitive opinions of area salesmen on the ground.
Right, the people actually talking to the customer.
Exactly. A single salesman's intuition might be skewed by a bad week, But if you aggregate the intuition of 100 salesmen and adjust it for environmental uncertainties, you often capture complex market realities that a simple math formula from headquarters might completely miss.
Okay, so the Delphi method and S-curves are fantastic if I'm an executive planning a 10-year factory build. But what if I'm just a regional warehouse manager? I don't care about the commercial viability of fiber optics in 20 years.
Right, you have more immediate problems.
Yeah, I just need to know how many pallets of inventory to order for next Tuesday or how to set my daily production schedule. I actually have hard, recent historical data. How does the math change when we look at the near future?
Well, when you have recent, reliable historical data, you move into near-term methods based on averaging. The most foundational of these is the moving average. The underlying logic is highly practical. You assume the demand for the next period will be roughly the average of the most recent periods.
Right, and the sources outline the formula for this, and it's actually quite elegant. It just rolls forward. To calculate your new moving average, you take your old moving average, add the actual demand from the newest period that just happened, subtract the demand from the oldest period you're dropping out of your window, and divide by the number of periods. It's like a sliding window moving across the timeline.
It is mathematically convenient, yes, but it has severe limitations.
I can see one right away. If I'm just taking an average of what just happened to guess what happens next, that sounds exactly like trying to drive a car while only looking in the rearview mirror.
And if the road suddenly curves while you're only looking backward, you crash. The text highlights the exact mathematical weaknesses that causes. First, moving averages inherently lag a trend.
Lag. How so?
Well, if your sales are steadily climbing month over month, your moving average will always forecast a number lower than your new reality because it's constantly being pulled down by older, lower data. Second, they are completely out of phase with cyclic or seasonal data.
Right, right. And third, wouldn't it flatten out the extremes? I mean, if we had a massive, unprecedented spike in demand last Black Friday, throwing that into a 6-month moving average smooths it out so much that we might completely underprepare for a spike this year.
Precisely. It flattens the peaks of your demand patterns. So to fix the rearview mirror problem, businesses use a more sophisticated method called exponential smoothing.
But wait, if moving averages lag because of old data, why not just drop the old data entirely? Or, if I know last week's sales are way more important than sales from 6 months ago, is there a way to mathematically tell the model to prioritize the recent stuff without totally losing the historical context?
That is exactly what exponential smoothing does. It assigns a mathematically declining weight to past data. The further back in time a data point is, the less impact it has on the current forecast. And the text provides the specific mechanism for this, a smoothing constant known as alpha.
So alpha is essentially an amnesia dial for the model.
That is a great way to think of it. Alpha typically lies somewhere between 0.01 and 0.30. A higher alpha places much more emphasis on your recent data. If your market is highly volatile right now, you turn up the alpha. You're telling the model to be highly responsive to what happened yesterday and to rapidly forget what happened 6 months ago.
Okay, averaging, whether moving or exponentially smoothed, is great for knowing what happened and extending that line forward. But it still just looks at raw numbers. It doesn't know anything about the real world. Right.
What if a business wants to understand the why? What if they want to predict future shifts in demand before they even show up in an average? Here's where it gets really interesting.
To understand the why, forecasters build regression and causal models. First, regression models look at historical data to identify the underlying structural patterns. Is the demand constant? Is there a linear trend? Is it cyclic or strictly seasonal? Then they use statistical methods to fit a line to that pattern.
The text mentions the least squares technique for this. Just to visualize that for you, imagine a scatter plot of messy data points all over a graph. The least squares technique is basically snapping a mathematical rubber band straight through the middle of those dots, angling it so that the total distance from all the scattered dots to the line is as small as possible. It finds the truest path through the noise.
That perfectly describes the mechanism. But causal models, also known as econometric models, take it a massive step further. They don't just draw lines through past sales. They try to link the variable you want to forecast to its actual real-world drivers. Yes, The text offers a brilliant example regarding tire demand. If you manage a tire company and you want to forecast demand for a given month, you do not just look at past tire sales. You build a causal model that links tire demand to two entirely different variables: the targeted production of new vehicles coming out of factories and the total road mileage of existing vehicles already on the road.
Right, because new cars need new tires, and old cars wear out their tires based on how much they are driven. But how do you accurately measure the road mileage of every existing vehicle in the country? You can't just check everyone's odometer.
No, you can't. And this was my favorite part of the sources. The model uses a proxy variable. It estimates total road mileage by looking at total petrol sales over the last 6 months.
It's so smart.
It's an incredibly clever way to capture the hidden gears of the economy. If petrol sales suddenly plummet, you know people are driving less, which means fewer tires are wearing out on the asphalt, which means replacement demand is going to drop. You can mathematically predict the drop in tire sales before it even happens just by looking at the gas pumps.
It allows a business to see around corners. But uh, there's a major vulnerability here.
Right, I was going to ask about the blind spots. What completely breaks these models?
The major caveat, which the text explicitly warns about, is that forecasting fundamentally assumes the past system of chance causes will continue to operate into the future.
Chance causes.
Yeah. These mathematical models are built on the assumption of normal, continuous conditions. They fail completely under abnormal conditions. If there's a sudden outbreak of war, a massive earthquake, or a severe, unprecedented economic depression, the causal links snap.
Wow.
And people might still buy petrol for generators during a disaster, but they aren't driving to work, so tire demand drops anyway. The past is no longer a reliable prologue.
So, assuming the world hasn't ended, we've picked our model, we've gathered our data, and we've generated our forecast. But how does a business actually know if their chosen model is working on a month-to-month basis? How do they know if the causal links are slowly, quietly leading them off a cliff?
That brings us to the final piece of the puzzle: forecast control. You cannot just set a mathematical model and forget it. You have to audit the oracle. The primary diagnostic tool the text outlines for this is the moving range chart.
The sources outline the mechanics of this, and it acts like a tripwire. First, you calculate your error for each period, which is simply your generated forecast minus your actual demand. Then you look at the moving range of those errors. You set an upper control limit at positive 2.66 times the average moving range and a lower control limit at negative 2.66. It creates this boundary, this acceptable bandwidth of error above and below your forecast.
This raises an important question. Why 2.66, and what happens when a data point falls outside those limits?
Yeah.
That 2.66 multiplier isn't just a random math rule. It relates to standard deviations in a normal distribution.
Yeah.
It is a structural alarm bell.
Right.
The control chart tells a manager three distinct things. First, is the past demand statistically stable? Second, is the present demand actually following the past pattern? And third, if a plotted error point breaches that upper or lower control limit, the system flags it.
It's the exact mathematical moment a company realizes the world they built their business for no longer exists.
Exactly. As long as your errors stay within the 2.66 lines, your variations are just random, everyday noise. You don't need to panic. But the moment you step outside those lines, it tells you that the underlying demand pattern has changed so drastically that your current forecasting method is broken. You have to throw out the model and revise your entire methodology.
So what does this all mean? We've gone on quite a journey today unpacking the exact mechanisms businesses use to survive the future. We started with the subjective bias filtering psychology of the Delphi method, moved through mapping decades of exponential tech growth and market saturation with S-curves.
Right.
Then we zoomed into the granular daily math of exponential smoothing, unbending scattered data with least squares, and finding the hidden gears of the economy using causal models predicting tire sales based on petrol consumption. And finally, we looked at how to keep ourselves honest by mathematically auditing our own predictions with the tripwires of a control chart.
It's a comprehensive scientific toolkit for trying to tame an inherently chaotic world. But as we discussed, every single equation and logarithm in this text rests on one crucial, fragile assumption: that the future will, in some fundamental way, behave like the past.
Which brings up a final thought to leave you with. The sources are very clear. Strictly statistical models fail entirely under abnormal conditions. Sudden wars, drastic social upheavals, natural calamities. Looking at the reality of the world today, we seem to be entering an era defined by increasing global unpredictability and extreme climate anomalies.
Yeah, the world is changing fast.
It is. So, if the chance causes of the past are completely severed, will the strictly mathematical regression models of the 20th century become useless? Might the businesses of tomorrow be forced to abandon their algorithms and return to human-driven subjective tools like the Delphi method to navigate a world where the future no longer looks anything like the past?
That is a fascinating question.
Maybe in the end, we'll find ourselves needing those crystal gazers again, just with a much more rigorous scientific method for reading the glass. Thank you for joining us on this deep dive.